Hello everybody. Today we're going to be discussing parallel circuits and how to evaluate them. So we've already talked about Ohm's law and we've already talked about multiple resistors in a series. Now we're just going to be wiring them a little bit different, and the way that we're going to be wiring them is in parallel. So this is an example over on the right. So here we have put more than one resistor in our circuit, and specifically they are wired in parallel, meaning that each resistor has equal access to voltage. And that's going to be key for our definition of parallel circuits, is that means that it's equal access to voltage. Now, the way that this circuit diagram is drawn, it also fits the geometry definition of parallel, namely one's on top of the other on top of the other. But this is just a diagram, a representation of what's going on. In reality, this could be any shape that it could be in, but all having the same access to voltage. So again, the definition of resistors in parallel is equal access to voltage. Don't get confused with the geometry definition of they're all going the same direction. So the voltage supplied by the battery is giving each side of the circuit, so the left side and the right side, the same electric potential, which means that across each resistor there's the same potential difference, that they have the same access to voltage. So the voltage across each resistor is the same. And this is the way that your house is wired. The potential difference between each side of the electric plug is 120 volts. The only difference is that the voltage source is the power plant that's like 45 miles away. So it's just a really big circuit. But what matters is each side of the power plug has the same potential difference, which means that every time that you go and plug something in, you have that same access to voltage. So all of the lights that are around me right now are in fact wired in parallel. And the other great advantage is not everything needs to be turned on at the same time. So let's take a look at an example of this. Here I have a circuit that's the same circuit that was drawn in the diagram with the addition of the light bulb on the top. So right now we have a battery that is giving all of these resistors the same access to voltage. And we can turn the current on and we can see how the electrons are flowing. Now, because the light bulb's on a switch, nothing is flowing through that light bulb. But if I throw the switch, now the light bulb turns on and we've got current flowing through that as well. But because we've all got the same access to voltage, the other resistors are unaffected. And we can see that if I open this back up. This has a number of advantages because all the components in this circuit are independent of each other. Let's say that this down here, this resistor, were to break. The light still remains on and unaffected, so this means that if one element in your house gets turned off, the others are not affected. So you can turn the lights out in your living room and the TV is going to stay on, and vice versa. You also then don't have to worry about making sure that you've got the right voltage going through everything and therefore balancing everything out to make sure that all the lights stay at the same brightness. One other thing with this is that you can notice that the current through all of these, and we can go ahead and connect this back up, adds up. So the total current down here at the battery is much bigger than all of the individual currents. And you can probably imagine putting lots and lots more into this circuit that's going to cause a bigger and bigger load. This could then start triggering the circuit breaker. For instance, in my kitchen, I can't run both my coffee maker and my toaster at the same time. Otherwise, that's going to overload the circuit and cause the circuit breaker to go pop and my bagel to stay cold. So let's now talk about how we're going to evaluate these circuits. So, most circuits that we have and deal with in life are running in parallel. I just used my kitchen as an example. I just used these lights as an example. Most things in life are actually run in parallel. And that just means that they have that equal access to voltage. In our houses, that voltage just happens to be 120 volts. So, everything is run in parallel in our houses. So everything that uses electrical power has a resistance and could be drawn as a resistor, just like what we saw in our series circuits. If I were to draw a circuit diagram of my kitchen, I would have one resistor for that coffee maker and one resistor for that toaster and another resistor for the computer that is also currently plugged in my kitchen. So, and knowing how much power each component uses is necessary to make all the electrical devices work. I just talked about what happens if too many things are plugged in and running at the same time. That can cause the circuit breaker to go pop and everything to shut down. So, we need to then calculate the current and voltage and resistance of all of these various different things, and just like last time, we're going to use a table. So, this is the same table that we used last time for series circuits. The only difference is now up in that upper left-hand corner, rather than an S to stand for series, I've got two parallel lines to show that what we're dealing with is a parallel circuit. And we're going to see that we're going to use this very similarly, but with a couple of small little differences. All right, so let's go ahead and get started. Here we have the circuit that was drawn earlier. So we've got a power source of 6 volts, so we got that 6-volt battery sitting in there, and we've got 3 resistors. We've got a 6 ohm, a 4 ohm, and a 3 ohm resistor. So over on the right-hand side, I went ahead and filled in all of my givens on the table. So I have my 3 resistors, and which resistor is A and which resistor is B doesn't matter at all, because this is just the way that I happen to draw it. Remember that this shows connections, not the actual wires, so this could be in any form of configuration that you could imagine. Usually, though, just as a naming convention, I am going to start with A being the closest one to the battery and go out from there. But again, it really doesn't matter. All right, so now let's see what we can do. We know that all the voltages are the same. That's the very definition of a parallel circuit, is all of the resistors have equal access to voltage. Now, we can go ahead and use Ohm's law to find the individual currents. So, we know V equals IR, voltage is all 6, the resistances were also given. We can go ahead and solve for I. So that's what I've got down here. So the current going through A is 2, the current going through resistor B is 1.5, and the current going through resistor C is 1. Now, as we saw on the simulation, the current going through each of those resistors, well, they are all splitting off from the main branch. So that means that the total current, the current that's going in and out of the battery is equal to the sum of all of those individual currents through their individual resistors. So we can go ahead and add that up. So 2 plus 1 plus 5 plus 1 is 4.5. So our total current is going to be 4.5 amps. And if I go to my circuit breaker in the utility closet, one thing that I can find there is that the circuit breaker that operates my kitchen is 15 amps. So as long as I keep all of the things plugged in around my kitchen less than 15 amps, I don't have to worry about causing problems. Now, let's see how we're going to add up resistors in this series circuit. All right, so how are we going to add resistors in parallel? So we know that the total current is equal to the sum of the individual currents. We also know that Ohm's law says that the current is equal to the voltage divided by the resistance. So we can go ahead and plug that in for all of the currents in our equation, and we get that the total voltage divided by the total resistance is going to equal the voltage across number 1 divided by the resistance of number 1, the voltage across number 2 divided by the resistance across number 2, the resistance of number 2, then you get the idea. So now we also know that because this is wired in parallel, all of those voltages are going to be the same, so they can go ahead and cancel. And this is going to leave us with the equation for adding resistors in parallel, which is going to be 1 over the total resistance is going to equal 1 over R1 plus 1 over R2 plus 1 over R. You get the idea. So let's see how this works in practice. So here we go with our circuit table and our equation for finding the total resistance. Now, you should notice that this is going to be 1 over the total resistance. So we're adding in reciprocal and then taking the reciprocal. It's going to be important that we end up finding the total resistance at the end of this and not just 1 over the total resistance, because that would be a problem. So let's go ahead and start filling in our givens on this. So 1 over 3 ohms in this case, plus 1 over 4 ohms, plus 1 over 6 ohms, and all of that's going to equal 1 over our total resistance. So now what we have here is something that we've got mixed fractions. So we can find our least common denominator. In this case, that's going to be 12. So our total resistance is 4/12 plus 3/12 plus 2/12. And all of that is going to equal 9/12. So 1 over our total resistance is going to equal 9 divided by 12 ohms. We're not done yet, because what we need to fill in on our table is the total resistance and not 1 over our total. So we need to take the reciprocal of this. So from the previous slide, we got 1 over our total equals 9/12 ohms. We can then take the reciprocal of both of those, and we get the R total is going to be 12/9. That simplifies to 4/3 or 1.33 ohms, which we can now go ahead and throw into our table. The easiest way, though, to solve for this in a calculator is, rather than deal with 1 divided by 1 divided by 1 divided by, is to go open parentheses, R1 to the negative 1 plus R2 to the negative 1 plus R3 to the negative 1, close parentheses, and take that whole thing to the negative 1. Because negative 1, that's just the same as 1 divided by the number, or taking the reciprocal. So this is a much more calculator-friendly way of typing it all in. So now we come back to the table, we can fill in that 1.33, and as a check to make sure we didn't screw up, we can go ahead and verify with Ohm's law at the bottom. So 4.5 plus 1.33 is going to give us a voltage of 6, so we did this correctly. With that, you now know how to add resistors in parallel and evaluate these parallel circuits in order to find the current and voltage going through each of these resistors. You could also then find different unknowns if you end up having a circuit with slightly different givens. With that, I wish you the very best of days.